All right, Calvin Ho, homework 15, starting in reverse. So, question 10, we're given this 3-inch disc. We're given that angular velocity 2. This one right here is 4. The angular velocity 1 here is 5, and we know that this theta is 30. So we're asked to determine the acceleration of point P on the rim of the disk, so right here. Okay, so right here are givens. Angular 1, 5, angular 2 is 4, so overall angular velocity is this 5I plus 4K. Taking into consideration that the XYZ frame of rotation has an angular velocity of 5I, so this whole frame is spinning 5I. So we know that the angular acceleration is this 5I crossed with this velocity, and we know that that equals negative 20j for the angular acceleration. So with theta equals 30, this point P here from the origin we know is 3 inches because it's 3-inch radius of sine 30, and this should be cosine 30. And to find the velocity at point P, we just cross our angular velocity with point P, and then we get this here. For acceleration, we cross the angular acceleration we found with point P, but we also add the angular velocity times the velocity at point P that we know. We found up here. And once we do that, we add them together, and this is what we get. Pretty easy. So moving up. Question 9, we're given this rig going on. At this instance, we know that at A, this rod of A has an angular velocity of 5 in the counterclockwise direction and angular acceleration of 2 in the clockwise acceleration. And we're asked to determine the angular velocity and angular acceleration at B. So our givens right here in the K, negative 2 in the K, and we know this length is given as 0.2 m. We set up our diagram, so we make I in the positive x, j in the positive y, and this K is going positive counterclockwise. So pretty easy. We're just going to find this angle of PBA. 180 minus 70 is 110. The angle of right here of APB is 180 minus 25. Minus is 110 we find earlier because we know this triangle has to be a total of 180, and we know this angle has to be 45. Okay, and then using that, we just use the law of sines to find the lengths. So we know this length AP is this right here, and that should be meters. Change this meters, and we know this is meters. And then with that knowledge, we can find the radius here of P from A is this, and the radius of P from B is this. Okay. With that knowledge, we can find this velocity at P is angular velocity of AP crossed with R P of A. So this R here, we get this. We know the acceleration is the acceleration of AP, that bar, crossed with RPA, and we're subtracting this angular velocity squared across RPA. And we know that we get this right here, just with that rotating fixed arm, rotating fixed frame. Then right here, if we think of in respect to this BPD, we can do same similar thing, and we're just notating that here. Same thing, WPB crossed with RPB, get the velocity, and we do the exact same thing as we did above for the acceleration. Then right here, if we look at P is a particle and it's going across BP, then we can create these equations. Velocity is just the sort of u times sine 20 coming from this angle here to finish this 90-degree angle, cosine 20, and acceleration, we just take the dot of u times it by the same thing. So to find the velocity at p, so we know that this total velocity at p has to equal the component that comes from v as a particle plus the component that comes from the BP portion of it. And we set up our equations, one's for I, one's for J, and solving those we're able to find this U here, and then we are able to find the angular velocity BP, which is 7.8612 rads per second. For the acceleration, we do a pretty similar thing, but we need the Coriolis acceleration that we use with our formula here, and that we find. We set up our equation. Total acceleration at P has to be equal to this part of P acting as a particle plus the part that comes from BP plus that Coriolis acceleration. That should be A. Do the same thing, set up an equation for I, equation for A, and then we solve it, find this U dot factor, and then we know the acceleration of BP has to be this 81.146 meters over second squared. Sorry, that's wrong. That should be radians over second squared. So we know that it's this radians over second squared. Since these are both positive, they're both going in the counterclockwise direction. All right, next question, question 8. We have kind of the two discs going on, drum right here and the one right here, and we know this inner one is attached and does not slip. 5 inches from G, 3 inches respectively, and we're asked to determine the accelerations of point A, B, and C. Okay. And we're given that the velocity of D here is 8 inches per second to the left, and the acceleration of C is 30 inches per second to the left. So we just set up our kind of a frame. So positive here, in this case positive going clockwise to match the spinning of the wheel. So right here, we know that the velocity of B is also 8 inches per second, since this is a parallel line right here, and they are in line with each other. And if we imagine at this instance that A is an instantaneous center with B, then we can actually find this angular velocity is 4 radians per second. So with that, go over here and we find that the acceleration of A right here, we can set that equal to our angular velocity squared times RAB from right here. And we can do this because this is a non-slipping, so we can use that equation. Find is 48 inches per second squared. Okay, and then for acceleration of B, we know it has to have 30 inches per second squared to the left, but we need to find this vertical component, and then the acceleration of G here is going to be going to the right to match the spinning of the wheel. So yes. So we're going to look at this point A with respect to B, and the acceleration A with respect to B is the acceleration at B plus the AP tangent component and the AB normal component. We know at A here, all the acceleration has to be going up since this is a non-slipping wheel. And then there's a zero component going into the in the J region. So with that knowledge, we grab all our components for X, 0, negative 30 to the left, times 2, the angle acceleration at A, times 2, that's the AB, and we find that the angle acceleration at A is 15 inches per second squared. And if we look at A with respect to G, we use pretty much the exact same equation, set it up the same way. X components together equals 0. AG right here, we take our angular acceleration, plug that into the equation, and we find that AG acceleration from G is 45 inches per second squared. Now, we are going to look at B with respect to G. So B with respect to G. We set up our equation for B with respect to D is acceleration G, tangent component of B to G, normal component of B to G. Plug in our values, and we find that the acceleration at B is 85.4 inches over second squared at 69.4 degrees. Do the same thing with C. C with respect to G, set up the same equation, acceleration at G, and then CG. The CG tangent and the CG normal. Just gonna fix this. Perfect. Plug in our values. We find we get 82.8 inches per second squared at 65 degrees. Perfect. Okay. All right, for question 7, we're given this frame here. We know that this crank here, BC, has a constant a constant angular velocity of 45 RPM going clockwise, and we're asked to determine the acceleration at A and the acceleration at D. Okay. So with that, we convert our angular velocity at BC, this 45 RPM, to radians per second. We have 4.7124 radians per second. We know since it says it's a constant angular velocity that the acceleration is 0. We can find our theta here pretty easily just with our sine rule, equals 30 degrees. We know this velocity at B with respect to C is this, we can use our 4 inches here times our angular velocity, and we get 18.8496 inches per second going upwards since it's turning clockwise. And then we know the velocity at A is the same thing since they're on a line. They're connected. Okay. So with that being said, we can find our acceleration at B as this right here instead of this equation. We know this j component is 0 since the acceleration is 0. So we just do our 4.7124 to the power 2 times 4, and we get 88.827 upward. Erase this. Okay. We do the same thing with respect to b, with a with respect to b, and we set it up acceleration AB, the AB tangent plus the AB normal. We know that in the x direction, at A it has to be 0 since it's wedged between this and moving up. So we set that up and we're able to find that our angular acceleration at AB is negative 12.821 radians per second squared. We set up the y and we find that AA equals negative 51.284 inches per second squared. And since it's negative, we know that it's just moving counterclockwise based on our diagram. Sorry, not counterclockwise now. Okay. Then we do the same thing with D with respect to B. Set it up here. So we know that acceleration D is AB plus acceleration of B, plus the acceleration of dB tangent and dB normal. We set this up right here. Get this, and by solving it, we get 184.9 inches per second squared at an angle of 16.1 degrees. Alright, problem 6. Problem 6. For this one, we're given these 3 gears in the arms, A, B, and C. We know the angular velocity of that arm is 4 radians per second going in the counterclockwise direction, and we know the angular velocity of this gear B is going 8 radians per second in the counterclockwise direction. And we're asked to find the instantaneous centers of rotation of gears A and C, as well as the velocity, the angular velocities of both A and C. So the easiest thing we can do is start with the arms. We know it's 0.3 meters on both sides. We know that the angular rotation of the arm is the 4 meters per second, 4 radians per second. And then we know that, we know that it's the 4 radians per second. And with that, we're able to find the velocity at both A and C here. Just a pretty simple distance times the velocity. So this 0.3 arm times the 4 for the angular velocity, 1.2 meters per second down here at A. And C is the same 1.2 meters per second going up. Next, we just look at gear B itself, since that's the one we have the most information about. We draw the same kind of diagram at this point here. We know from the contact point of B to C is 0.1 meters, and from B to A is 0.2 meters, so we make this velocity 1, velocity 2. Do the same kind of formula, because we know the 8 radians per second angular velocity here for B. So 0.2 times 8 is 1.6 meters per second down, and this instantaneous velocity at 2 is 0.1 times 8, equals 0.8 meters per second going up. So next we draw just kind of our velocity diagrams of gear A. And we have this V1 at the edge and VA in the middle. We know that the angular acceleration of A is this 1 minus A divided by the radius, which is 0.1, and we get 4 radians per second. And then we can also find that the instantaneous center for A is the 1.2 here. So this 1.2 divided by 4, the 4 radians we found up above, and we get 0.3 meters. Do pretty much the exact same thing for C. We know this this angular velocity of C is 1.2 minus 0.8 divided by 0.2 for the radius. We get 2 radians per second, and the instantaneous center of C equals 1.2 divided by the 0.2 radians we found above. The 2 radians we found above, and we get 0.6 meters. Alright, here's question 5. So this one, we're given some 6-inch radius wheels that we know roll without slipping on the horizontal surface. We know this distance here from A to D is 5 inches, and we know this distance here from B to E is 4, and then this D has a velocity of 6 inches per second to the right, and we're asked to determine the velocity of E. So first down, we just write down what we know. This VD equals 6 inches per second. We can find the angular velocity at this point D by just taking that velocity of D divided by the radius, and we get this 1 radians per second. Next, we go on to find the velocity at this point A, which we know is this radius of RA times the angular velocity we just found. We take the 5 here plus the 6 to get 11. We times it by the 1 radians per second, and we get 11 inches per second. This next one, we're just going to look at this wheel E. We know this radius from B as theoretical point Q. We choose this point Q because it's the simplest point on the wheel to work on, because we know all the acceleration has to be going up. So we know this radius here is negative 4I and 6J. And then to find the velocity at B, we're going to take this angular velocity of E times it by that radius we just found, and we get this kind of dummy holder for now that we're going to use later on. We switch over to looking at the actual bar A to B here. We know that the RB of A equals the square root 171I minus 5J. To find that velocity of the bar, we're going to take the cross of the what we call angular velocity of AB times the radius we just found, that R we just found, I'm sorry. And then we're going to get this right here. And we know that the velocity of B with respect to A has to be the velocity A times the velocity of BA. And we're going to plug that in as well. And then we're going to combine this velocity b that we just found with this other one we found here and set them equal to each other because we know they have to be equal. We're going to separate by the i's and get this equation here, j's and get this equation here. By solving them simultaneously, we get angular velocity of AB equals 0.7527 radians per second. And this angular velocity of E is negative 2.4605 radians per second. Then to find the velocity is simple. We're just going to take this angular velocity of E and cross it by the R we found above, the REQ. By solving that, we get 14.76 inches per second towards the right. So this next one, question 4. We're given this contraption. We know that at the instant at this point that the velocity of DE is 2.4 radians per second going in the clockwise direction. So this DE, angular velocity going in the clockwise direction. We're asked to find the velocity at A and find the velocity at B. So we just write down what we know. Since we know most about this d bar, we're just going to find the velocity at this point d, and all we're going to do is times this angular velocity times this radius de, and we get 0.22 meters per second in the j direction. Next we move over to look at this section here, A to D, and we notice this collar here. So we know that the R from A to D is this 0.08, 0.150 down. Yeah, 0.150. And then we're going to find the velocity of A with respect to D is the velocity of D plus velocity of dA. And we know that by solving that, we get this 0.22, 0.080 W angular velocity of AD in the J minus 0.150 angular velocity AD in the I. For this J, since we know that it can only go in the I direction, we know it has to be equal to 0. So we can solve for WA, angular velocity of AD is negative 3.6 radians per second. And then we're going to bring that back and solve for VA right here. And then for the components in the I direction, and find that VA velocity at A has to equal 0.540 meters per second in the positive I direction. So that's our velocity there. We're going to look over from this D to B. From this drawing and the dimensions we're given, we know that that RDB it equals negative 0.4 RAD, and then we get this here just because putting 60 over 150 we get that 0.4. We're going to do our velocity of B with respect to D, that equation, plug in what we know, solve it, and then we get 0.457 meters per second, 61.8 degrees going over into the second quadrant. All right, we got question 3. We're given this disc is moving in the x and y plane. We're given some initial component velocities. So, for example, this velocity at A, we're given the y component. This velocity B, we're given the x. This velocity at C, we're also given the x. We're asked to determine A, the angular velocity of the disk, and B, the total velocity at point B. So for this, we're gonna start with our radius RBA. We know 6 in the I, 6 in the J. Take the velocity of that. So negative 0.6 times the angular velocity plus 0.6 times the angular velocity in the J meters. We do the same thing for C to A, which we get is 1.2 I, and we get 1.2 W in the J direction. And we're going to look at this velocity B with respect to A. So velocity B with respect to A is velocity of A plus velocity of B of A. We're going to split it up into separate components. We get this equation for the I, this equation for the J. We're going to do pretty much the same thing with C. Break it apart, and we actually get that in this I coordinate, we get negative 1.4 equals V A component. So this velocity A axis component is negative 1.4. We can split that velocity C into its J, and then we get this VCY component. Using the equations from VB, plugging in this velocity AX component, we're able to find that the angular velocity is 10 radians per second. With that, we're able to plug that 10 radians per second into our J equation, this VBY equation, and find that that is negative 1 meters per second, and we finish by writing the full velocity of B equation, which is negative 7.4 I minus 1 J meters per second. So this next one too, we're given these gears is lifting this load. We assume that gear A starts from rest, it accelerates uniformly to 120 RPM in 5 seconds, and then maintains a constant speed of 120 afterwards. We're asked to determine the number of revolutions executed by gear A to raise the load and the time required to raise the load. So we just take that 20 feet, convert it to inches to match all our other measurements. We know that the theta B required to move the load all the way up would be that 240 times divided by the size of that B gear, which is 15. So we get it needs to move 16 radians. And then we calculate the circumference travel using the equation that RA times theta A, RB times theta B, this theta required to be, and this R size of A, and we get 288 inches for that circumference travel. Then to find the theta A that's required, we just take that 288 inches divided by that R of A, and we get that the required movement of the A gear is 96 radians. Divide that by 2 pi, and we get 15.28 revolutions is what that A gear needs to move. So for part B, we can calculate the angular acceleration of A by taking the final speed, which is this 120 RPM, minus the initial, which we know is 0, and the time it takes to get there, which is 5 seconds, and we get 2.5133 radians per second squared. So we know this theta. This theta of A, that it needs to move to get the at that time after 5 seconds is 31.416 radians, so that is position. The change once it has the gear all the way up, we know the final position is 96 radians from the step before, so we minus that sum we used and we get 64.584 radians is the additional movement up. So we can take that theta that additionally moved up divided by the angular velocity, the final angular velocity, which is this 120 RPM, and we get that the time it changes from that 5 seconds to get the load all the way up is 5.139 seconds. Add that to the 5 seconds we already went up, and we get about 10.14 seconds is the time to lift the load all the way up. Okay, so final question. We're given these two pulleys. I just gave them positions here, so it's a little easier. But yeah, we're given two pulleys. There's 3 different positions. We know that the angular acceleration of shaft A is 6 radians per second squared, and the system initially starts from rest. And we need to determine the time required for shaft B to reach 400 RPM with the belt in each of the 3 positions. Yeah. So we start with what we know. Angular acceleration of A, 6 radians per second squared. We know that we need B to get to 400 RPM. That's about 41.889 radians per second. And we know this angular velocity of A is the angular acceleration times time. We know that the speed of the belt, the velocity of the belt, equals the radius of A times the angular acceleration of A, angular velocity of A, and it could also equal the radius of B, the angular velocity of B. We plug in what we found earlier for angular velocity of A and solve that for T, and we get the radius of B over radius of A times 41.889 divided by 6. Then we can translate that to equal the diameter of B and the diameter of A. Because since they're over each other, it's just a ratio, so it's fine to put it in like that. But for this first position, 2 over 4, we get 3.49 seconds. Position B, we get 3 over 3, which is 6.98 seconds. And C, which is 4 over 2, we get 13.96 seconds.